Imagine, just for a second, a microscopic drop of water.
Right, just a single drop.
Yeah, a tiny drop of water and a few hours of unprotected air. Now imagine that literally destroying a titanium medical implant before it's even finished being made.
It's crazy to think about, but yeah, it happens.
I mean, think about it. You're running a multi-million-dollar manufacturing facility, right? You've invested hundreds of thousands of dollars into state-of-the-art machinery that is capable of extreme, like microscopic precision.
Oh yeah, massive capital investment.
Exactly. So you install it, you power it up, and you expect it to run flawlessly, but then bam, your production line is brought to a catastrophic halt.
And it's not what you'd expect either.
Right. Not by a fire, not by a structural collapse, not even a software glitch.
Yeah.
It's brought down by an invisible, creeping enemy. Moisture.
Moisture, oxygen, and time.
Yeah. So today, our deep dive is taking us into a highly specific, honestly fascinating technical manual detailing rust prevention on CNC deep hole drilling machines.
Which is quite the specific topic, I know.
It is. And, for those who might not spend their weekends reading industrial manuals, CNC stands for computer numerical control.
Right.
Essentially, these are machines whose movements are entirely driven by program software, meaning they operate with absolute calculated precision, supposedly with zero human error.
Supposedly being the key word there.
Yeah, exactly. So our mission today, we want to uncover how that cutting-edge manufacturing precision actually relies on a surprisingly simple, ancient battle against moisture.
And what we can learn from it, right?
Exactly. We're going to look at what this level of rigorous, systematic maintenance can teach you about protecting your own high-value investments, whatever they might be. Okay, let's unpack this. Because it turns out the line between a perfectly machined part and a catastrophic factory shutdown is, well, it's microscopic.
It really is a battle of scale,
Yeah.
And to understand the magnitude of the problem we're dealing with, we have to look at the physical environment these machines operate in.
Right, because this isn't just drilling a hole in the wall.
Oh, not at all. Deep hole drilling is not like taking a standard cordless drill to a piece of drywall in your living room. I mean, these are massive industrial behemoths boring perfectly straight, incredibly deep channels into solid blocks of steel.
So the forces are just huge.
The physical forces involved are immense, and the precision required is absolute. The source material makes it incredibly clear. Surface corrosion on this high-value equipment isn't just an aesthetic issue. It's not just, oh, it looks ugly.
Right.
It's a structural virus. It accelerates mechanical wear, it fundamentally compromises the integrity of the metal, and it depreciates capital assets faster than almost anything else on a factory floor.
Wow. Okay, so before we get into the complex ways engineers actually stop the rust, we need to understand the underlying mechanics of the destruction it causes.
Yeah, the chain reaction.
Right. Because for a lot of people, rust just means like a slightly brown, rough patch on an old bicycle chain.
An annoyance, really.
Yeah, just an annoyance. But here, the manual treats it like a pebble in a marathon runner's shoe. It's just a tiny patch of oxidation on a massive block of engineered steel. Why does a little rust actually matter?
Well, the marathon runner analogy is actually perfect for understanding the physics here.
Yeah.
Because think about it, a pebble changes the runner's entire gait.
Oh, sure. You start limping.
Exactly. Which puts stress on a knee, which then tears a ligament, which ends the race.
Ah, I see.
It's a violent chain reaction. At a molecular level, rust is just iron reacting with oxygen and water to form iron oxide.
Okay, basic chemistry.
Right. But that iron oxide is physically larger and much more brittle than the base metal.
Wait, it's larger?
Yeah, it expands. So it expands in flakes, which fundamentally alters the surface roughness of the cutting tool.
Okay, so the tool isn't smooth anymore.
Exactly. Now remember those extreme high-load forces I mentioned earlier?
Yeah.
When you take a cutting tool with a rough oxidized patch and force it into solid metal, you introduce a microscopic anomaly in friction.
Like hitting a speed bump.
Precisely. That uneven friction causes the tool to violently shake and vibrate during deep cutting. Engineers call this phenomenon chatter.
So the tool is essentially bouncing around inside the hole instead of slicing cleanly through the metal.
Yeah, which completely undermines the purpose of a precision machine. I mean, that chatter physically changes the diameter of the hole being drilled.
Oh, wow.
Suddenly the part fails its straightness inspection, the surface finish is completely ruined.
That's bad.
But the chain reaction gets worse. That localized rusty spot actually weakens the metal's structural strength, acting as what engineers call a stress riser.
A stress riser.
Yeah, it's a tiny pit where all the extreme physical forces of the drilling concentrate. So under heavy load, that microscopic pit is pulled apart and it quickly becomes a physical crack.
Oh, man. So it just snaps.
The crack snaps the tool off deep inside the hole, which then violently jams the main components of the machine itself.
A completely cascading failure.
That is wild.
Yeah.
And, reading through this manual, another detail really caught my attention.
About the flakes. Yeah. The rust isn't just staying attached to the tool and causing vibration. Because it's so brittle, it's actively flaking off during the whole process.
Right, and the detachment of those flakes introduces a completely different mechanical failure.
How so?
Well, in deep hole drilling, something called chip evacuation is the single most critical factor for success.
Chip evacuation, okay.
Yeah. You're generating incredibly hot, sharp metal shavings, the chips, down inside a dark, confined channel, and they need a high-speed, clear path to escape the hole.
Right, you have to get the waste material out.
Exactly. Those microscopic rust flakes act like a dam in a river. They physically wedge into the tool's flutes and block the chip removal channels.
Oh, I see where this is going.
Yeah, so now the hot metal chips cannot evacuate. They pack tightly together, the friction spikes the temperature exponentially, and the tool essentially welds itself right to the workpiece.
That sounds like a nightmare. And if those flakes don't jam the tool, they cause an entirely different, highly expensive problem for the factory owner.
The contamination issue.
Yes. The manual explicitly outlines how these rusty flakes flow through the system's fluids and end up sticking to the clean workpiece being machined.
Which is a disaster.
A total disaster.
Yeah.
We're talking about high-precision medical parts here. You cannot have rust contamination on like a titanium bone screw or a surgical tool meant to go into a human body.
Absolutely not.
The manual notes those expensive parts must be thrown straight in the garbage.
What's fascinating here is how the source material links a microscopic chemical reaction directly to the factory's financial bottom line.
Yeah, it's not just a technical glitch.
Not at all. The direct effect of flakes on a workpiece is a dramatically increased scrap rate.
Right.
You're constantly forced to buy replacement tools, your machine is offline for maintenance, and you're throwing away incredibly expensive finished goods.
So much wasted money.
The financial multiplier of one tiny flake of uncontrolled oxidation is staggering.
Okay, so if a single flake of rust on a drill bit causes a medical part to be scrapped, then the absolute most dangerous time for that tool is the moment it leaves the safety of the machine and hits the open air.
It's incredibly vulnerable.
Right. And reading the manual's guidelines for protecting tools immediately after use, I have to admit it sounds deceivingly simple.
Oh, I know what you're going to say.
It talks about washing the tools with a solvent, using a soft brush, and drying them off with a soft cloth. I mean, honestly, this sounds like doing the dishes.
It does sound like that, yeah.
Isn't that a bit basic for advanced robotics? Like, how does an industrial solvent wash differ chemically from just standard cleaning protocols?
Well, it's a common misconception that this is just about removing dirt. We're actually dealing with highly specialized chemistry designed to achieve rigorous environmental isolation.
Okay, so it's not Dawn dish soap.
Definitely not. The manual is absolute on this point. Improper storage of exposed, untreated tooling accelerates rapid oxidation, degrading precision cutting edges within hours.
Wait, hours,
Ugh.
not days or weeks.
Not months, not weeks, hours. If you leave a wet tool sitting on a bench, the atmospheric water begins reacting with the iron immediately.
Wow.
So the washing phase uses specific industrial solvents that are chemically formulated to displace water.
Okay.
They wash away the metal chips and the dirty coolant, sure, but they also break the surface tension of any remaining water droplets, actively driving moisture away from the microscopic pores of the metal.
So it is actively neutralizing the chemical environment on the surface of the tool rather than just, making it look clean.
Exactly. And you must wipe the tool completely dry because any residual moisture left behind becomes a localized galvanic cell for rust to form.
A galvanic cell, basically a tiny rust battery.
Exactly. And the manual is incredibly strict about where that tool goes next.
Right, for storage.
It must be placed on a ventilated rack. You're instructed to never put tools on a wet floor.
Which makes sense.
Yeah, because a wet factory floor creates a microclimate of localized humidity. That moisture will evaporate, drift upward, and aggressively attack the bare metal.
So the tool is chemically neutralized, dried, and elevated. But the manual mandates another layer of defense before the tool is put away, applying anti-rust oil.
The oil is crucial.
And it highlights that this requires a highly specific chemical matching process.
Right. The anti-rust oil acts as a thick physical barrier against atmospheric oxygen and water. But the crucial detail from the text is that you cannot just use a generic lubricant.
No WD-40 here.
No, you must match the specific chemical properties of the oil to the metallurgical makeup of the tool itself.
Okay, give me an example.
So if you're using high-speed steel, commonly known as HSS, you need a mineral oil formulated with specific corrosion inhibitors that bond well to that alloy.
Makes sense?
But if you're using carbide tools, which have a completely different porosity and surface chemistry, you need entirely different specialized oil formulas.
Wow.
You meticulously brush this oil over every single cutting edge and then store them in closed boxes to completely lock down the local atmosphere around the tool.
Okay, but for operations that don't want to rely entirely on an operator brushing oil onto every microscopic edge, the manual dives into advanced factory coatings applied directly to the tools.
Right, the tin coatings.
Yeah, they detail titanium nitride, or tin coatings. This creates a highly stable, permanent chemical skin over the tool that physically blocks water from ever touching the underlying steel.
It's an incredible piece of material science. The titanium nitride essentially seals the vulnerable steel inside an inert vault.
And here's where it gets really interesting.
Yeah.
The manual notes that this titanium nitride coating, this impenetrable vault, measures between 1 and 5 micrometers thick.
It's insanely thin.
Right, just wrap your head around that scale. A single strand of human hair is about 70 micrometers thick.
Yeah.
We are talking about a protective chemical skin that is a tiny fraction of the thickness of a hair, yet it completely halts a catastrophic, factory-ending chain reaction.
It perfectly illustrates the microscopic scale of this battle, you know? The protection is invisible to the naked eye, but the stakes are massive. But focusing solely on the tool forces us to look at a much larger vulnerability.
What's that?
Well, protecting the drill bit inside a closed box with advanced chemical coatings is entirely pointless if the machine holding that tool is actively sweating water onto it.
Right. We have to move from the micro level of the tool to the macro level of the entire factory floor.
The whole environment.
Yeah. When I was reading the strict environmental guidelines for the workshop, the only thing I could compare it to was like a cigar humidor.
I like that analogy.
So to protect the machine, we basically have to put this massive factory floor inside a giant humidor.
The humidor analogy is structurally very accurate. The manual explicitly states that unregulated ambient humidity and temperature fluctuations inevitably lead to condensation directly on the exposed cast iron machine beds.
Okay, so it sweats.
You have to understand the physics of cast iron. It's incredibly dense and has huge thermal mass.
Meaning it holds temperature.
Exactly.
Yeah.
If the air temperature in the factory warms up quickly, that giant block of metal takes a very long time to catch up. It stays cold. Ah, I see.
So as warmer, humid air hits that cold iron, it hits the dew point, instantly turning the machine into a massive magnet for condensation.
Wow. It is literally pulling water right out of the air and depositing it onto the most vulnerable surfaces.
Which is why the factory itself must become the armor.
Right.
The rules are absolute workshop humidity must be strictly kept between 40 and 60%.
That's a tight window.
They mandate the installation of large industrial dehumidifiers to actively strip moisture from the room's atmosphere. Maintenance teams have to check coolant tanks constantly and stop leaks instantly.
Because even a puddle matters.
Yeah, because a puddle on the floor alters the ambient humidity of the entire room.
Unbelievable. And even with the air completely dried out, the daily physical maintenance of the machine table is intense.
Oh, the vacuuming. Yes. The manual requires using an industrial vacuum every single day to remove wet metal chips. Because if you leave wet chips sitting on a bare metal table overnight, you're trapping localized moisture against the iron, restricting oxygen flow in that specific spot, and setting up a miniature rust factory right on the surface.
If we connect this to the bigger picture,
Mm.
you start to see that every square inch of the machine requires a distinct, specialized strategy.
Right.
The large stationary parts of the machine bed and the columns are encased in incredibly thick epoxy paint.
Because they don't move.
Right. Epoxy creates a heavy, impermeable physical barrier. For other stationary components, they use chemical phosphating.
Phosphating.
Yeah. Instead of just painting over the metal, phosphating forces a chemical reaction that grows a crystalline protective layer directly out of the steel itself.
That is super cool.
Mm.
But paint and crystalline layers only work on parts that don't move.
That's the catch.
The manual introduces a major challenge with the machine's guideways. These are the massive precision ground tracks that the heavy machine components physically slide back and forth on.
Yeah, you can't paint those.
Right, paint or phosphating would just scrape right off under the immense weight and friction.
Exactly. Those guideways are bare sliding metal, making them the most vulnerable point on the entire machine.
So how do you protect them?
Because they must remain bare to slide accurately, the manual solution is active, continuous lubrication.
Pumping grease.
Yeah. You must regularly pump fresh, incredibly thick anti-rust grease into the machine's tracks. This grease serves a vital dual purpose.
It lubricates.
Right, it provides the hydrodynamic lubrication needed for heavy metal parts to slide smoothly, but it also creates a dynamic moving seal.
Oh, clever.
It physically repels water, pushing it away from the bare iron as the machine moves.
Which brings up a really massive contradiction in the manual's logic.
Oh.
I mean, we have just spent all this time obsessing over keeping water away from the machine.
We have.
We're vacuuming chips, we're chemically sealing the metal, we're aggressively dehumidifying the air. But during the actual deep hole drilling process, the manual states we're pumping massive amounts of liquid directly into the hole.
Flooding it.
Yeah. Wait, we just spent all this time keeping water away from the machine. But during drilling, aren't we pumping massive amounts of liquid directly into the hole? Doesn't that cause rust?
It's the ultimate paradox of industrial machining, honestly.
Right.
You're terrified of moisture, yet the physics of drilling require you to flood the cutting zone with liquid to cool the tool and flush out the chips.
It feels wrong.
But the manual clarifies the specialized chemistry of what is actually being pumped. It's not raw water.
Okay, good.
It's an emulsified cutting fluid engineered specifically for machining steel parts.
Okay, so it is a carefully balanced mixture of oil and water packed with chemical rust inhibitors. But wait, if the manual stresses that the concentration of this fluid must be strictly monitored between 5 and 10% oil, that means 90 to 95% of that liquid is still just water.
That's true.
How does a tiny fraction of oil manage to protect the bare metal from the massive amount of water it is literally swimming in?
It comes down to how an emulsion functions, like at the microscopic level.
Okay.
In a properly mixed 5 to 10% emulsion, the oil doesn't just, float on top. It forms these microscopic droplets called micelles.
Right, micelle.
Exactly. And
Yeah.
they're suspended evenly throughout the water.
Okay, so it's a homogeneous mix.
Yes. When that fluid hits the hot metal of the machine and the tool, those chemical rust inhibitors and the oil droplets are drawn straight to the metal surface.
Oh, wow.
Yeah, they coat it in a microscopic hydrophobic film before the water can even react with the iron.
It is creating a liquid force field on the fly.
That's a great way to put it. But that chemistry is highly volatile.
Meaning you have to maintain it.
Exactly. If the mix falls below 5%, it becomes what the manual calls a weak mix.
And then the force field fails.
Precisely. There simply aren't enough oil micelles and chemical inhibitors to maintain that barrier. It breaks down, and that 95% water is suddenly free to violently attack the bare metal of the machine and the tool.
And it needs to do a lot of heavy lifting. I mean, the manual dictates that a massive volume of this fluid is pumped into the hole under high pressure.
Right, it's not a trickle.
It's designed to wash the extremely hot, wet metal chips away instantly, basically blowing them out of the hole before they have a chance to stick, cool down, and start rusting against the valuable machine parts.
This raises an important question, though.
What's that?
We've focused a lot on protecting the tool, the machine, and the fluid. But what about the raw material itself?
The block of steel.
Yeah. You're doing everything right, but what if the giant block of raw steel you're about to drill into is already compromised by the environment?
Oh, man. Because if you push a perfect, microscopically coated, chemically oiled drill bit into a block of steel that is already covered in a thick layer of hard, abrasive rust,
It's going to be bad.
that rust is going to act like coarse sandpaper. It will grind against the tool and destroy the precision cutting edge instantly, regardless of your oil and coatings.
Which is exactly why the manual details strict pre-treatment protocols for the raw work pieces before they even touch the machine.
They treat the raw block first.
Yes, raw steel blocks that are prone to rusting can be put through a chemical bath to alter their surface properties.
What kind of bath?
Well, they might use a phosphating process, which, as we discussed earlier, forms a hard crystalline skin on the block.
Right, right.
Alternatively, they use a passivation process.
Passivation, what's that?
Passivation is fascinating. It's essentially an acid bath that strips away the free iron from the surface of the metal, leaving behind only the corrosion-resistant elements like chromium.
So it changes the chemistry of the surface.
Exactly. This tricks the metal into forming its own microscopic dense oxide layer that blocks any further water from interacting with the vulnerable iron underneath.
That is wild. You are fighting bad, uncontrolled oxidation with good, chemically engineered oxidation.
Fire.
You create a clean, chemically stable workpiece so that the delicate tool stays safe throughout the entire grueling drilling cycle. It really is an incredibly complex system where every single variable is deeply reliant on the others.
It's entirely interdependent. I mean, think about it. If the fluid concentration drops to 4%, the protective nacelles fail, the tool rusts, chatter begins, the hole is ruined, and the expensive medical part is scrapped.
All from a 1% drop.
Yeah, and if the ambient factory humidity spikes to 70%, the dense cast iron sweats, the guideways corrode, the machine loses its precise alignment, and the factory shuts down.
Wow. We have covered a massive amount of technical ground here.
We really have.
Let's look at the ultimate mission of this deep dive. Stopping an invisible enemy like rust on these multi-million-dollar machines requires a holistic 360-degree approach.
It really does.
It's about actively neutralizing the chemical environment of the tools immediately with specific solvents and storing them on elevated, ventilated racks. It's about understanding the thermal mass of your equipment, keeping the workshop air strictly between 40 and 60% humidity, and physically vacuuming up wet chips daily.
Don't forget the fluids.
Right, and it's about actively maintaining the delicate molecular balance of your emulsified cutting fluids right at that 5 to 10% sweet spot, while chemically pre-treating your raw materials.
It's a full-time job.
It really is.
Yeah.
So what does this all mean? For you listening, you might not have a CNC deep hole drilling machine sitting in your garage.
Probably not.
But this deep dive is really a masterclass in systematic maintenance and systems thinking. It shows exactly how addressing incredibly small, invisible vulnerabilities, like the chemical makeup of a fluid or the ambient humidity in a room, prevents catastrophic, vastly expensive breakdowns in the long run.
Absolutely.
It is about controlling your physical environment before the environment inevitably controls you.
It really fundamentally changes how you look at maintenance and systemic failure, you know?
Cool.
We've just seen the incredible obsessive lengths engineers go to in order to control the physical environment, monitor the chemistry, and prevent an invisible reaction from destroying a multi-million-dollar process.
Yeah.
It makes you wonder if a massive, heavily engineered factory can be brought to its knees simply because the ambient humidity changed by a few percentage points. What invisible, unmonitored systemic variables are quietly degrading the tools and systems we rely on every day, like in your own mental or digital environments?
Think about that. You invest so much time and capital into building high-functioning, capable systems in your own life and work. Don't let an invisible, creeping vulnerability bring it all down just because you weren't watching the environment.
Keep an eye on the humidity, basically.
Exactly. Keep your systems tightly controlled. We'll catch you on the next deep dive.